way I normally do it. So welcome to the November 2018 Planetarians web seminar. And today with the recent successful landing of the InSight on Mars, we have an unusually timely talk by our special guest, Justin Filiberto, who is a staff scientist at the Lunar and Planetary Institute. His topic for us is volcanism in the inner solar system, not just Mars. And without further ado, I think I'll turn it over to you, Justin.
Cool, thanks. So let me try sharing my screen. Can everyone see my slides and only my slides?
Yes, we can see your slides.
Perfect. So thanks. So I'm going to talk about volcanism in the inner solar system, tour of volcanoes on Mars, Venus. I have Mercury in gray because I'm probably not going to have time to get to it, but if you have questions, I can talk about it. And I'll focus a little bit on the moon as well. If there are other questions, I have some slides on the outer solar system as well, on Io, Enceladus, and Europa. Very different volcanism out there. So if anyone has questions, we can go through some of that after. But I will not get through every volcano in the solar system in 25 minutes or so. So in order to study volcanoes in the solar system, the best place to start is the Earth. We know more about volcanoes in the Earth than we do any other planetary body. We can go measure them. They're active, and so we can see what processes we have on the Earth and use those as analogs for studying places like Mars, Venus, Mercury, and the Moon to tell us about what's going on in the interior, what's going on the surface and making the volcanoes. So let's talk about how we make a volcano on the Earth and the two main classes of volcanoes on the Earth as we move out to other planets. So Planet Talk, we're going to talk about the Earth as our baseline, and then we're going to focus on the inner solar system, Venus, Moon, and Mars as well. So volcanism, this is a nice cartoon from an intro geology textbook, but volcanism is just the surface expression of what happens deeper. And so we've got the interior of the Earth, we have our mantle. It's a solid interior, but it's convecting, and it's releasing heat, and the way it releases heat is through volcanism. And on the Earth, we have two main types of volcanism. We have what's called decompression melting, where parts of the interior of the Earth are coming straight up. As they come up, the way that they're releasing their energy is by melting. And that's producing magma. And this is what happens at places like Hawaii, our hotspots, where material is coming all the way from the core mantle boundary to the surface. Another example is ridge systems here. I don't think my pointer's coming up, but where two plates are pulling apart, magma is going to then, or the interior is going to move up, fill its place, melt, and produce magmatism there.
Justin, we could actually see your cursor. So
oh, you can. Oh, perfect. So
it's
right
pretty
here.
small, but we can see it. Yeah.
Okay. So we've got two plates pulling apart. As these pull apart, the material underneath the mantle comes up. As it comes up, it starts to melt. This produces the magma, and this is what produces the magmatism at the ridge systems. Not shown on this picture are hotspots where we've got material coming up from deeper all the way to the surface without plates pulling apart, and that's places like Hawaii. The other type of melting we have in the mantle is where we have recycling of crust. And actually, this is important for today, where we had a magnitude 7 earthquake in Alaska. But here we have West Coast, we have a plate colliding with another plate. This is an oceanic crust. This is continental crust. The oceanic crust is denser. It gets recycled down. It does not remelt, but it volatilizes. So it releases water and CO2 and sulfur and chlorine into the mantle over it, which melts and drives volcanism. And so in our subduction zones, places like Mount St. Helens and Japan and Alaska, these are much more explosive volcanism. This is where we have CO2 and water-driven melting, so a lot more volatiles coming off. And so when we look at, excuse me one second. Sorry about that. As we look at the structures that these volcanoes make, they make very different volcanic landforms. And so here's a nice, this is now out of date since the eruption over the last year, but we have a nice big picture of Hawaii. We've got very gentle slopes. The two main types of lava here, this is called Pohoihoi, this is called A'a. They're relatively liquid in both cases. You can see one outrunning here. And this is from our plume melting. And so we've got heat. So here's the core, here's the mantle, and here's the crust. And we've got heat from the core mantle boundary coming up. As this comes up, it melts the mantle and we produce our shield volcanoes. These are dominated by these black rocks called basalt. And this will be important when we leave the Earth and go to other planets. On the other hand, our composite or stratovolcanoes, these are from our subduction zones. These are dominated by ash. So here's Mount St. Helens in 1982 after it blew the top off. The rest of these are Sulphur Hills, St. Augustine in Alaska, and Popocatépetl in Mexico City. These are much more explosive. They're much steeper slopes, and you can see the magma here and the rocks around here are lighter in color. They have more silica in them. And so between the amount of volatiles and the higher silica content, we get a lot more explosive eruptions. And so the big difference here, so we look at what's going on. We've got our subduction zone, our oceanic crust going down. This is in contact with seawater before it goes down, so it's altered. It's releasing this water and the CO2 here, melting the mantle. This magma then rises and produces the volcanic arc, which are typically ash deposits with some lava thrown in. If we look at the slopes of these two types of volcanoes as well as the heights, and so here is a comparison of shield versus composite volcanoes. This is in meters, and you can see it's significantly vertically exaggerated. But you can see here's two hotspots, Krafla and Hawaii, so Iceland and Hawaii. We've got two subduction zone volcanoes, Etna, and I took Mount Hood because Mount St. Helens blew its top off, and so it doesn't quite work well for this comparison. And you can see Hawaii and Krafla, so our hotspot volcanoes, are typically bigger than our subduction zone volcanoes, and you can see the slopes are a lot shallower. In the vertical exaggeration, they don't look all that different, but when we start adding other planets on there and other volcanoes from other planets, you'll see the big difference. But these have much steeper slopes than the shallower slopes of Hawaii and Krafla. If you've ever hiked a volcano, Hawaii is a lot easier to hike around than trying to climb the steep slopes of Mount Hood. So those are the two main types of volcanoes. We have a lot of other smaller types. We have things like cinder cones. You can see it here. This is one magma chamber that sort of just erupted on top of on the surface. This is relatively basaltic magma, but a little bit cooler. And so it didn't make nice lava flows like in Hawaii. These typically forms on the side of volcanoes, and actually we'll see one of these when we go to Mars. The one that makes the news all the time over whether or not it's going to erupt is Yellowstone. Here's the giant caldera, and this is a caldera complex where the volcano is so explosive it doesn't even produce a landform, it just makes a hole in the ground. And then we can have things where they interacted with water, like tuff rings, and you can see it here. There's a whole lot of other different types, but we're really going to focus on the two main types as we go to the other planets. All right, so Venus. If I'm moving too fast, or if you have questions, please feel free to stop me and ask questions. So when we move to Venus, we have to remember that we don't have imaging of the surface. And so this is what Venus looks like if we take images, and what you mostly see is that cloud deck. And so it's carbon sulfur atmosphere and a very hazy atmosphere. However, we can see to the surface with radar. And so we have radar images covering the entire surface. They're not the exact same as imaging because radar is So these bright spots can be elevation. It can also be change in physical properties, so a change in chemistry or mineralogy. It can also be porosity and density. But we can use models to figure out the height, and we can look at some of the volcanoes and some of the volcanic structures on Venus and compare them to the Earth. So this is one of my favorites. This is Olympus Mons. You can see the cool thing about radar is it actually highlights the lava flows for you. The brighter they are in this case, the younger they are, the darker they are, the older they are for this volcano. This is because as they age, they darken. So you can see the nice lava flow structure, and you can see how far it stretches out. You can see some that go all the way out here and all sorts of in this direction. So you can actually see one going off in this direction. Olympus Mons is 400 kilometers across. It's 1.5 kilometers tall. It has very long lava flows and a slope of about 0.5 degrees. And so this is consistent with places like Hawaii, where we get these nice long lava flows. If anyone was watching the flank eruption a few months ago, that went kilometers long, all the way out to the sea before it dropped into the sea. Here, we don't have a sea to worry about, so they just keep going. But a very shallow slope, 0.5 degrees, and rather tall. Now, the one thing I'll note on the next slide is when you get an image or you get data like even the data I showed you, you always have to look for vertical exaggeration because it may tell you something very different. And so this is Map Mons, and I usually fly the images on the right, but this is the JPL image. And if you didn't know it was 20 times vertically exaggerated, you say, this is really steep, and this looks like a subduction zone. However, if you unexaggerate this image, this is what it looks like. Almost flat. Very, very shallow slopes. And this is it zoomed in as well. You can see a nice long lava flow coming at us in this direction. So again, even though the press image makes it look like these very tall, steep-sloped stratovolcanoes we have on the West Coast, Map Mons, again, like Olympus Mons, is consistent with a Hawaiian volcano type. We do have weird volcanoes on Venus that are not consistent with sort of Hawaii. We have something called pancake domes. And the reason that they are called pancake domes is because they look like a pile of pancakes. So you've got very round structures, and they have very steep slopes on the edges of them. And you can see this one's got caldera complex in the center, or crater complex in the center. You can see a couple over here. These cracks are tectonic features that broke them up later, but you can see these. These are interpreted to be single flows, very steep sides. They're about 0.5 to 1 kilometer in height. You can see they're about 20 to 30 kilometers across. So the question is, what are these? Are these basalts that somehow got contained, and then they'd be consistent with what we're seeing with other volcanoes? Or are they rhyolites or silica-rich magmas, which would be a lot more consistent with things like subduction zone or recycling of our crust? And the answer is we don't really know because we only have them in surface morphology. We see them in radar, they're bright, they've got these steep slopes. We don't know much beyond that. They are consistent with things like rhyolite, so rhyolitic flows do form these where the material comes up and glassy dome structures. But we also have this example on the right from Earth where we've got steep slopes and a flat top, which is actually a cold crystal-rich basalt. So it's telling us that the magma that came out was very sticky, but it's not telling us about composition. And composition is what we really need to know about in order to figure out how they formed and if there's recycling or anything going on in the interior. Unfortunately, with only radar, we're not going to get there. We need to have a new mission to Venus to either get spectroscopy measurements of these, or more likely to get a lander on or near one of these pancake domes.
I've got a question about those. Hello?
Yes?
Yeah, I'm curious, is there a theory about why they're so uniform in size?
So if you look at similar structures on the Earth. We do find them about the same size. It's the fact that they're all about the same size tells us that whatever process formed them was the same for all of them. And so the temperature of eruption, the density, what's called viscosity, or how easily a magma moves, the chemistry was probably the exact same for all of them in order to get such similar features of about the same size.
Thank you.
So on Venus, we also have all of these little structures. And you can see all of these little volcanoes dotting the surface. You can see one here. These are low cones, and this is lava plains. So this is a lava flow with all of these low cones dotting it. They're a few kilometers in diameter. This is 5 kilometers across an inset. You can see one here. You can actually see the structure perfectly with the crater here. Again, with only radar, our best guess is that either these are a field of small shield volcanoes, or I'm going to go back for a second. These cinder cones, where we've got steeper slopes and that nice wide mouth. Structurally, they're either very, very, very small versions of Hawaii or a field of cinder cones. And based on imaging alone, it's hard to sort of constrain that until we actually get there. So if we look at Venus and the Earth, and we use my scale here, and you can see the scale has changed. This is in meters. We're up to 500,000 meters and 4,500 meters, so you can see our vertical exaggeration. The green lines are Earth, and now on blue is Venus. And it's interesting that the shield volcanoes on Venus, Theia Mons and Sapis Mons, are both about the same height as Krafla in Hawaii, but they're even larger. And they have even gentler slopes than Hawaii, which has now sort of shrunk down in here, and Mount Hood, which is near vertical, and Etna as well, near vertical. The reason for this is just the temperature of the surface, also the amount of material that comes up. In places like Hawaii, we have plates that move across our hotspots. And where the plate has moved, we make a line of hotspot volcanoes, or the Hawaii tract. That's why we have multiple islands there. On places like Venus, and we'll get to Mars, we don't have our hotspot tract. We don't have plates moving on top of our hotspot, and so we can produce these huge volcanoes. And you'll see when we get to Mars that they get even larger than this compared to the Earth. But the same process that formed a volcano at Hawaii, at Krafla, is producing magma, or was producing magma at Theia Mons and Sapis Mons. Apologies if I put you on mute. I'm getting over a cold and still have a little bit of a cough. So let's move to the moon. We can see the moon here. You can already see 2 different colors. The 2 different colors make up 2 different rock types on the moon. On Earth, we've got 2 different types of crust. We've got basaltic crust in our oceans, and we have our granitic crust, which makes up our continents. For the moon, the original crust, shown here in gray, is not granite like we have here, but a rock called anorthosite, which is made of mostly one mineral called plagioclase. And this actually tells us how the moon formed. We're not going to focus on that because that's the early process. We're going to focus on all of these black areas and the volcanism and the magma that came out later. So we can see the Mare Plains. This is all volcanism. This is all lava flows that erupted. You can see a channel here. This is how the magma sort of moved along the surface. It's not from water. These are later crater impacts that impacted into the Mare. These are basaltic rocks, just like we have at Hawaii. We also have channels through these, and so you can see here a nice long lava river channel. Here's an astronaut, actually, and the rover sitting in one of these channels, taking samples. So this is where magma would have flowed through. It melted the rocks underneath as it was flowing through, and then continued out of the channel on the other end, just like water in a river, and leaving this channel behind. We do have some evidence for small volcanoes and small volcanic structures on the moon. This is Greithausen domes. You can see one up here. You can see another here. These are 20 kilometers across. They're 1 to 2 kilometers tall. An average 7-degree slope with the steepest up to 20 degrees. And you can see Marius Hills, and you can see the Greithausen domes here. And if we look at our slope again, they actually have a steeper slope more consistent with subduction zones. These are not subduction zones. These are actually smaller than these. These are not subduction related volcanism, but they actually are in some cases thought to be felsic, so silica-rich magma, and this came from recycling and remelting of the bottom of that original crust, producing felsic or felsitic magmas. And so that's why we're getting a steeper slope and sort of more localized volcanoes. So a little bit different than the processes that form volcanoes on the Earth and Venus. Oh, and you can see here Venus is removed because if it's not, Greithausen domes disappear. You can see the larger image here, and Greithausen is more or less a vertical line at the bottom. So we're going to move to Mars, my favorite planet, and importantly, the one we're about to learn a lot more about its volcanic history when we start getting data back from InSight. You can see Mars here. Immediately, you can see the 3 volcanoes blown up here in gray, and then Olympus Mons, the largest volcano in the solar system. So we'll jump straight to Olympus Mons. You can see here, you can see a nested caldera complex in the center. This tells us that there were repeated patches of magma and different magma chambers that moved through the area. If you went to Hawaii and looked at Hale-Malmal crater, although at the moment you can't because the observation deck is closed, but if you could look there, you'd see a similar feature where you've got different caldera complexes, and the craters fell in with different batches of magma coming into the magma chamber. It's 640 by 840 kilometers across. It's 21 kilometers tall with an average slope of 5 degrees. That nice gentle slope consistent with Hawaii and Hawaii type volcanism. This is a giant basaltic shield volcano sitting on the surface of Mars. If we move to, if we zoom in with some of the higher imagery on the flanks here, and you can see it here, you can see all, we've switched back to imaging and not radar, but you can see all of the lava flows. This is 3 kilometers across. These are incredibly long features, very consistent. You can see this one goes on for kilometers, and I could trace multiple of these 4 kilometers long. This tells us the magma that came out was very runny. It kept moving, it stayed hot, similar to what we see on Hawaii. This is a smaller one. This is Tharsis Tholis. For whatever reason, this is one of my favorites. You can see here, this is not a caldera related to volcanism. This is actually an impact into the structure after it formed, giving us a somewhat of an age date for this. You can see the caldera complex here. This is a nested one where there's one inside of a larger one. It's 150 kilometers across, 8 kilometers tall. Again, a nice shallow slope. If we go to Syrtis Major and we start looking at the flanks, and I didn't show a picture of Syrtis, but this is the flanking. You can see here what's remnant of a volcano. And if we followed it across, it would have a nice, very large, round depression in the center, and would have a 30-degree slope, so very, very steep slope. And then you can see that it's surrounded by lava flows that came out after this formed. And we do see this on Earth. This is a broken cinder cone where we had a vent we had the remnants of the cinder cone here. This is Red Mountain, and then the lava flow would have come out this direction, and the rafted cone material came out here. And so this is very common on Earth, where a cinder cone starts forming, and then a lava flow will break out the side. This is on Mars, and start flowing in this direction, breaking apart parts or half of the cinder cone as the magma goes off. And so this again tells us it's basaltic magma, and a very similar process to what we see on Earth. If we look at our slope diagram, you can see this is my favorite because it actually, the vertical slope is a little bit better. We're now 25,000 meters to 500,000 meters, so we're off by we're about 20 times vertically exaggerated instead of almost 100 times vertically exaggerated. The Earth, you can now see nicely the difference in slope between subduction zone and hotspot volcanism. You can see how weird Venus is with these very, very gentle slopes, but similar heights. And then plotted here are 3 examples for Mars, Tharsis, Tholos, Mons, and then the behemoth Olympus Mons. And you can see that while we're 4 times larger than Hawaii, you can see that the slope of this line is the exact same as we move out into larger and larger and larger volcanism. And you can see here now Greifhausen looks very similar to his subduction zone, even though it's not subduction related, but it's because it's stickier, more silicic magma. All right, so InSight. InSight landed on the 26th, so Monday. Some background of InSight, you can see this is the first image that InSight sent back. This is all dust on the dust cover, so they haven't removed the dust cover yet. This was to protect it during landing. But even with this, you can see this is also a fisheye lens, which is why the horizon is so exaggerated, but the horizon's here, the sky's up here. This is the ground. Over here, you can see one of these feet. Where it landed, it has 3 feet. And then you can see a small rock. This is the mission itself. There are 2 major instruments for volcanology and geophysics on here, a seismometer and a heat flow probe. So what's going to happen is the solar panels are already out and fully deployed. Over the next month and a half, this arm is going to start deploying instruments and doing a check. It will then take these 2 instruments, which are currently sitting on board up here, off, put them on the ground. This will then have a cover. This is the seismometer. This is the heat flow probe. The heat flow probe, or the press has been calling it the mole, will then start tapping itself down into the ground and measuring the heat coming out from the crust. Here, the seismometer will then start looking for Mars quakes. And if we get enough Mars quakes, we may be able to see whether or not there's still magma in the interior. We may be able to see how volcanically or geophysically active Mars currently is. And so even though we're nowhere near a volcano, this 2 instruments will help us tell what the heat is coming out, and that can tell us about the heat in the interior, and this will tell us about how active the interior is and whether there are things moving, how quickly. And then this, was there a question?
Oh yeah, I was going to ask how deep that probe is going to go.
A couple meters, not that deep.
Thank you.
And then this is the other image that was taken. So this is from that deck, and you can see the instrument sitting here. This is the grappling hook that's actually going to deploy the instrument. The great thing is we landed in a nice, dusty, rock-free area, which makes putting a mole down, trying to dig into this, and a geophysical probe sitting on this much easier. We don't have to worry about dealing with large boulders like you can see over here. And a lot of this is just the blast zone from the rockets from this landing, but you can see this will make deploying these instruments a whole lot easier than if we were sitting right next to that large rock. So that's InSight. We won't have data for a while. Seismic networks are great, but you need to listen to the interior for a long time. And so we'll be getting data over the next, or once it's deployed, it will be a year of listening and then understanding the data. So I think I'm good on time. 6 o'clock. So some inner solar system summary, with the exception of Mercury. Basaltic magmas really dominate the volcanism in the solar system. We have some evidence for rhyolitic or much more silica-rich magmas, but almost everything we've seen is these nice basaltic things. And shield volcanoes are the most common on terrestrial planets. So Hawaii really is our best analog when we go to other planets. Subduction zone volcanoes, like we see on the West Coast, we see in Alaska, have only been found on Earth so far. We don't see evidence for recycling. We don't see evidence for large-scale plate tectonics once we leave the Earth. And so using stratovolcanoes are interesting, but shouldn't be our focus going forward. And that tells us a lot about sort of planetary dynamics and how planets are put together, and it tells us that Earth really, at least in our solar system, is unique. I will leave it there and happily take questions, and if anyone wants to see a slide or two about Mercury, or we can go out to the outer solar system, I have some of those as well.
Oh, thank you, Justin. I invite everybody here to unmute and turn on your camera if you like, and let's have a round of applause for Justin. That's really wonderful. I'm going to stop the recording just for a moment here. Actually,